We now do lecture C2, the final part of lecture C. In C1, I believe we left off at, we were doing differential calculus. We had just finished the univariate uh, calculus, and now we're moving on to multivariate calculus. The idea here now is that you have a function y in terms of many x's, so perhaps x1 through xn, and only one y, many x's. That's the value of the function initially, for any given value of x's. Now what you imagine is that one of these x's, not all, just one of these x's changes by a tiny amount, let's say xi, changes by a tiny amount, delta x, xi. Now you, just like before, you ask what's the change in the function. So here's the value of the function at the new value of x's minus the initial value of the function divided with the change in xi. And now you imagine sending xi off to 0. What's left over is the, when you take limits, is the partial derivative of the function with respect to xi. Partial because you're only finding out the change in the slope, the change in the function, divided by the change in one of the xi's, holding all else equal. And you notice the notation has changed. This is the partial derivatives notation. So here's an example. This left side is exactly what you saw in the previous slide, just reminding you that when you take partial derivatives, you're changing one of the x's. Here's a function in 3 dimensions. So it's the z plot is your y, and then you have two quote unquote x-axes, x1, x2. Here's the equation right here. First of all, what's the slope of the function from the perspective of x1? So what this means is for any given value of so take for example, look at it from this perspective, right? From the perspective of x1. When I look at the mountain this way, all slopes facing me are slopes that tell me the change in the function with respect to x1. If I look at the function this way, I'm asking for the slopes of the function with respect to x2. To get just the slope of x1's, when I differentiate y with respect to x1, I'm holding x2 constant always. So if I do so, when I differentiate with respect to x1, this becomes 10. That becomes minus 2x1. And since this does not contain any terms in x1, both of these become 0. So that's the slope of the function with respect to x1 holding x2 constant. Similarly, what's the slope of the y function with respect to x2 holding x1 constant? Since there's no x2 here, this goes to 0. There's no x2 here, that also goes to 0. There is an x2 here, this derivative becomes 20. That derivative becomes minus 4x2. So you'll notice that there were no cross terms in x1, x2, right? So this gives you the slope seen from the x plane. This gives you the slope seen from the x2 plane. In general, when you have a function with many, many x's, you can define the following quote unquote creatures. First of all, there's a gradient vector. The upside down triangle is the universal symbol for the gradient vector, which is a fancy word for the vector of first derivatives, because first derivatives are slopes. Since you have n dancing x's, there must be n slopes. So the vector, so here's a slope with respect to x1, x2, x3, all with xn. This vector is called the gradient vector. And now if I take the slope of the slope, I get this second derivatives. But instead of being a vector, it now becomes a matrix called the Hessian matrix. Why? Because I can take here's the slope with respect to x1. I wonder what the slope of the slope is with respect to x1. So if I differentiate the first derivative of x1 with respect to x1 one more time, I get this feature right here. But I could take this first derivative of x1 and differentiate with respect to x2. That would give me the second element over here. If I kept going like this would be the derivative of the first derivative, the slope with respect to x1, differentiate one more time with respect to xn. So what you now have is a n by n matrix. So once again, in case you didn't follow this, this would be take the derivative with respect to x2 and differentiate one more time with respect to x1. Right? So slopes of the slopes. So these are n by n. They're always a square matrix by definition because there are n variables and there are, of course, n second uh, derivatives. You have to take n by n second derivatives. At first glance, you might say, well, if n became a very large number, let's say n was equal to 5, it looks like you would have to compute 25 separate terms. But thanks to Young, that's Young right here, I think, well, at least that's what Google says. Luckily, you don't have to compute all n by n squared elements. Because what Young says is that the Hessing matrix is going to be a symmetric matrix. And if you remember, a symmetric matrix says that the off diagonal terms are going to be exactly the same. So notice that anything that's ij and ji for all I and j's are going to be exactly the same, right? As long as I and j are not equal to each other, of course. So for example, f12 will be the same as f21, f1n will be the same as fn1. So you notice that from here, as soon as you find out f1n, I know that fn1 must be exactly the same. As soon as I find out f12, f21 must be exactly the same. So you really actually only have to compute for fewer terms than at first glance. An example. Here's an equation. Here's a vector of first derivatives, a gradient vector. So if I now differentiate this with respect to x1, I get minus 2. If I now differentiate with respect to this first line with respect to x2, I get 0. Here's f2. F2 differential is, well, I actually don't need to do this anymore because remember Young says, wait a second, you don't have to do F2 1 because F2 1 is 1 2. So as soon as I found out F1 2, right off the bat I can put it over here. So I am only left with, of course, computing F2 2. So take F2, differentiate one more time with respect to X2, and the answer is minus 4. That should be a type. Sorry guys, it's a typo. That should be a minus 4 right there. Oh, sorry. Life sucks. All right, next up, you have this function. Here's the first derivatives, the gradient vector. And once again, I now differentiate f1 with respect to x1. I get simply 8. I now differentiate f1 with respect to x2. I get 12. And then, of course, I know that has to be the same as f2.1. And now I have to compute f2.2, which, of course, is 18. And we're done. Now we do something called the implicit function theorem. So if you remember, there were some functions, I showed some to you last time, which are implicit functions. Here are 3 examples. So I'm going to change the notation a tiny bit. I'm sorry, you'll see why in a few minutes. Now what you have is an implicit function of y and several x's. And so now I'm going to collect all the x's and call them a quote-unquote vector x. And here's an implicit function where all these terms in y's and x's must be equal to 0. So in order for you to call this an implicit function, collect all the terms so that the only thing on the right side is number 0. So for example, if someone said y is equal to 3x squared, I could rearrange and get y minus 3x squared minus 0 is equal to 0. I don't know why I put 0 here. It's early in the morning. If someone has said x squared plus y squared is equal to 9, I could have rearranged and expressed in this implicit form. And this entire creature right here could have been equal to minus 3. If I brought the minus 3 over here, this would now be an implicit function in y, x's, and w's equal to 0. So all these are implicit functions. Is one yx, yx, and ywx. 2 topics that are worth noting going forward. First is, if you give me some function in terms of y's and x's, how do I really know that there is in fact that y is in fact an implicitly defined function of x, meaning that you give me a bunch of terms, but how do I know that y is in fact a legit function of, let's say, x1, x and w, right? So for it to be a function, every value in the domain must be assigned a number in the range, right? So how do I know this is actually happening? And the answer is given by the implicit function theorem. So we saw this last time. If you're given this equation as an example, you will notice that if you work it out, you will actually get y is equal to this plus and minus square root of x squared minus n. So with every value of x, you'll have 2 values of y. That's not a function. So we wonder, are there some values of x's? Are there some places where, in fact, y starts to behave as a legit function of x? Even worse, look at an equation like this. It's not that easy to isolate y in terms of x and w's. So given such an implicit function, if somebody asks us to compute the partial derivatives of y with respect to x and w, how would we do it? Because right now, the only technique we know is to isolate y in terms of x and w's and then carry out the partial derivatives. But since we can't do this, how would we carry out the partial derivatives? And the answer is given by implicit differentiation. So once again, implicit function theorem says, how do we know that once you give me an implicit function, the y's are somehow a legit function of x's? And give me an implicit function, how do I carry out partial derivatives? Even though I don't know the explicit functional form. Implicit function theorem says the following. It's a little bit a mouthful, but it's actually less scary than it looks. Consider an implicit function. A bunch of y's and x's is equal to 0. If this left-hand side has continuous partial derivatives, and there's some point out there, there's some values of y's and x's, where this left-hand side is equal to 0, and you have the partial derivative of y at that point equal to 0, then it is true that y is going to be a function of x. So one more time, there's a bunch of y's and x's. You wonder whether y behaves as an implicit function of x's. So first, what you need to do is you need to make sure the left-hand side has continuous partial derivatives. Second of all, there has to be some values of y's and x's where this entire expression is equal to 0. And third of all, at that point, if you differentiate this implicit function with respect to y, that partial derivative cannot be 0. Well, if it is not 0, then y is a function of x in that neighborhood of that point. Here's an example. Supposing that there's a planet that goes round and round and round around the sun. And now let's say the equation of this planet, its motion is given by this elliptical equation, 3x squared plus 4y squared is equal to 48. Right? So let's bring this over here. I'm going to call this left-hand side fyx. So now what you have is an implicit function of y and x is equal to 0. You already know by looking at this. So for example, if you pick this value of x, you notice that you have this value of x, you have two values of y. So you already know this is not a legit function. Right? A function is supposed to have, for every value of x, you're supposed to have one value of y. But now you have two values of y. So this is rather a correspondence, not a function. But you wonder, are there some regions, some neighborhoods, where it does start to behave like a function? So for example, if I had this ellipse, and somehow I got rid of these arcs over here, and I only worked with this arc right here, that would be a function. Because if I only worked with this arc right here, for every value of x, I would have one value of y. So I wonder if, given this entire ellipse, are there some places where in that small region, I can consider y to be a function of x. And just by looking at this graph right here, if I take a microscope and instead of looking at the entire ellipse, if I just narrow down, focus to this region, and this region only, extrapolating from everything else over here, this region only, y does behave like a function of x. Because give me a value of x, I'll give you a value of y in that region. But how would we prove this? Well, first of all, I need to check if this implicit function has continuous partial derivatives. So I take a partial derivative with respect to y. So differentiate with respect to y, you get 8y. That's good. I differentiate with respect to x, and I get 6x. And now so the partial derivatives do exist. And now I need to find a point where this equation is equal to 0. Well, that's true because, right, so by definition, any value of x and y on this ellipse will guarantee that this entire equation is equal to 0. Done. Now what I need to do is I need to find is this partial derivative of y, right, since this implicit function is 0 for all values of x and y. Now I wonder, give me any value of x and y, is this partial derivative is any place where it's not equal to 0? And you notice it's not equal to 0 at all places except when y is equal to 0. Well, but if y is equal to 0, that means that x must be equal to minus 4 and plus 4. So minus 4 and plus 4 are these regions right here. So what you're saying is that by the implicit function theorem, y is implicitly defined in this neighborhood because this point, in this neighborhood, the partial derivative of y is not 0. So I can treat y as a function of x over here. But in this space right here, where you have the coordinates 4, 0, I cannot treat y as a function over here, and I cannot do so at this point either, at minus 4, 0. And you should ask yourself, why not? What's so different about this and this? And the answer is, if you took a microscope and focused down here, for any value of x slightly to the left of 4, once again in that region, for that value of x, you have two different values of y. So you can see that you're trying to get away from this idea of having two values of y. You can do so over here, but you can't do so in the really small, tiny region around 4, 0 or minus 4, 0. So y does behave as an implicit function of x everywhere except near those 2 points. Pretty cool. What about implicit differentiation? Here's a nasty looking animal, right? And somebody says, listen, I want you to find out dy dx and dy dw, ceteris paribus. To compute this, you have to use something called total differentials and total derivatives. And total differentials are the multivariate cousin of what you saw earlier in univariate functions as a derivatives. To get you going, let me remind you, back in univariate functions, if y was a function of x, 1y, 1x, you know that dy dx is f prime x. And you know that I showed you that for tiny changes in x, you can express the total change in y to be equal to the partial derivative of x, not the partial side, the derivative of x multiplied by the change in x. This is total differential. That's actually derivative. Right? Now, what I now want to do is to get this creature right here, I have to extend these two things to multivariate cases. The next slide is hideous. Don't be scared. It's just a matter of having a clear head and taking it slowly. I'll go very slowly. Let's start with y as a function of x. I personally, if I was to teach calculus, in undergrad, I would start off by not teaching students how to take derivatives. Rather, I would tell students to do differentials. So, by differentials, supposing now y and x both change. You already know from the previous lecture the total change in y is equal to the derivative of f with respect to x multiplied with the total change in x. And you could have gotten this result by taking the derivative, right? And by rearranging this. I personally like going from the function to the differential. If I now divide by dx, the only variable right here, I get the derivative. That would be my personal preference. Sadly, undergrad profs go derivative, then differential. Okay. This is the chain rule that you saw in the previous lecture. Y is a function of x2, but x2 is a function of x1, which is y ultimately is a function of x1. Somebody says to you, give me the change in y due to a change in x. If you use a differential approach, what's the total change in y? The total change in y, see, is equal to the change in f due to the change in x2, right? So differentiate f with respect to x2, then multiply by the change in g due to x1, that's your g prime, multiplied by total change in x1. So you should really see the intuition behind this, right? So first, how did f change with respect to the g, and how did g change due to the x, and then what was the total change in x1? And if I now divide both sides by dx1, I of course get your usual classic derivative, your chain rule thinking. Now you have y in terms of several x's. All of them change simultaneously. The total change in y is going to be first a change in f due to x1, as your partial derivative of f with respect to x1, times the total change in x1, plus partial of f with respect to x2 times dx2, not shown here. And you keep going, 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 partial derivative of the f function with respect to the nth variable times the total change in xn. This is total differential. Now the trouble is you can't really get the derivative because for the derivative, only one of these things has to change. So for example, I imagine xi changes and everything else stays a constant. In that case, the total derivative would then be holding all other changes in x constant. If I now divide by dxi, I would of course get those expressions that you see over here, right? So, and then of course, since I'm holding all other x's constant, I could then of course send them off to zero, right? Or, sorry, let me backtrack that. Sorry. So let's go back here. So you have this expression right here. If you now have all x's changing and you only want to focus on the change in y over the change in xi, then you would divide by change in xi, and you have that expression. But now if you imagine that xi was the only variable changing and all the other x's were not changing, then all the other dx's have to be zero. So then dy dx will simply be the partial derivative of f with respect to xi, which is exactly what you saw earlier in the lecture. This is a slight extension. I'll give you an example of what this is in a few seconds. Now you notice that y is a function of x and w listed separately. Now wait a second. Two, one, here you're told that x is a function of w. So many people have asked previously if x is a function of w, and so I write it this way. So y is a function of x, which is a function of w, and w. Why am I listing these w's twice? And the answer is that you have to sometimes remind yourself, and I'll show an example in a few minutes, that x may be implicitly expressed in terms of w's, but w's may appear separately in whichever equation this is of y in terms of x and w's. So you're imagining the equation where y is in terms of x's and w's separately. So for example, you could say y is equal to x plus w. And then x itself is a function of w, so then you would say y is equal to gw plus w in that example I imagine. So you can't get rid of this w separately because it recognizes that the terms in w may appear separately from x in that primary equation up here. W changes and you wonder what the total change in y is. If you got the logic so far, the total change in y, well, first the change in f due to the change in g, that would of course will be your differentiate f with respect to the first argument. See, there's two arguments here. So f1 means differentiate f with respect to g. Then differentiate g with respect to w. That's your g prime. Then multiply by total change in w, dw. Plus, this is the, you can say I'm using this right here. Differentiate f with respect to the second argument, f2. And then, of course, multiply by change in w. Right? So, written out, it looks like that. Sorry, if I want to find dy dw, I can divide by dw everywhere, and that's the expression I get. Now let's make it even more difficult. You have x1 listed separately from x2 listed separately. So some equation up there where the term x1 appears separately, which means there must be a plus or a minus from x2, separately from w. x1 itself is a function of g of w. x2 is also a function of w. So now you have y as a function of x1, which is a function of w, x2, which is a function of w, and w separately. When w changes, what's the total change in y? The total change in y is first the change in f due to the first argument, that's f1, times the change in g due to change in w, that's g prime, multiply with the total change in w, plus the change in f due to the second argument, that's your f2, change in h due to w, that's h prime, times the total change in w, plus the change in f due to the third argument, which is f3, into the total change in w, which is right here. And of course, if somebody says give me dy dw, you divide throughout, and that's the answer right here. And this is now the worst case here. Notice how x1, x2 are here, and you have u and v. x1, x2, rather than now being functions of simply one w's, are now functions of u and w themselves. So x1 depends on u and v, x2 also depends on u and v. So y is a function of ultimately u's and v's. And you now have one argument, two, three, four. Right? Four. So if what's the both u and v change at the same time, what's the total change in y? Here goes. The total change in y is first the change in the f function due to a change in the first argument, that's the f1, times the total change in the g function, that's your dg right here. And by the way, what's dg? Well, the change in g must be because what happened was, since g is a function of u and v, the total change in g is the change in g due to u times the change in u plus the change in g due to v, gv, times the total change in v. Now, comma. Next comes the change in f due to the second argument, which is f2, times the change in h. And the change in h, of course, is the change in h due to u times change in u plus the change in h due to v, that's hv, times the total change in v. Carrying on, was a change in f due to the third argument, that's f3, times the total change in u plus the change of f due to respect to the fourth argument, f4, times the change in v. And now this is the total change in y when u and v change simultaneously. And if somebody wants to find out dy du, for example, holding dv constant, you would write this expression down. So, it looks very scary in the beginning, but if you actually just follow, this is the fundamental rule. As long as you follow, everything is basically a variation of these things right here. Right? Let's do some examples. Say y is a function of several x's. So you know that if all x's change simultaneously, the total change in y is, once again, the change in f due to the first argument times the change in the first x1 plus change in f due to the second argument, f2, times dx2, and so forth, and so on and so forth. This is, so when somebody says, using this trick right here, when somebody says you're given an implicit function, how do I calculate the change in y over the change in x? Just from this implicit function. Let's do a general rule first. Now imagine that both y and x are changing. But when they change, they have to change in such a way that the total change in the big F function has to be equal to 0. Right? So imagine now both y and x change simultaneously. And now what happens is, what's the total change in f? The total change in big F is the change in f due to the change in y, that's your partial right here, into the total change in y, plus the change in big F due to x, that's your partial derivative right here, times the change in x. And because behind the scenes x and y are intertwined in such a way so that this entire big F equation always has to be equal to 0, when you change x in such a way, y has to adjust in such a way that the total change in the f function is always left equal to 0. So this means I can express now this entire expression nicely. The partial derivative of f with respect to y times dy plus the partial of f with respect to x times dx. That whole thing has to be 0 because behind the scenes that function must be 0. So x and y must change in such a way that the total change is always equal to 0. Otherwise, this would not be sum of equal 0. And now if I take this expression and rearrange, voila, I get that dy dx is minus fx or xy. What this means is, if somebody gives you an implicit function, this thing right here, and asks you to find dy dx, this rule says put a minus sign, differentiate the left side with just respect to x, and then differentiate just the f function with respect to y. That will give the change in y over the change in x. Many students, by the way, when you are asked to, if you didn't have open book, tend to confuse this. They think that dy dx should be equal to minus fy fx. That's not true. The change in y over the change in x is equal to minus fx over fy. The things are reversed. Make sure you practice this. Example. Let's go back to the happy days of micro. Imagine a consumer has a utility function. Your utility depends on two goods, Q1, Q2. So here are, for example, the plots of indifference curves. Here's good 1 on the x-axis, good 2 on the y-axis, When you draw in different curves, it's really important to tell the reader which way the quote unquote, because these are curves correspond, these are the level curves of a three-dimensional utility surface. So was the surface rising northeast, northwest, etc., etc. So this arrow tells you that good one, good two are good goods in the sense that you're getting higher and higher utility going northeast. Someone gives you a particular point Q1, Q2 and says, give me the slope of the indifference curves at this point. So you imagine, of course, the graph has exaggerated this. I imagine a tiny change in good number one. And now if good one, number one changes a tiny bit, to remain the same indifference curve, I have to change good two in a very precise manner. So good two can't just change in any way whatsoever. It has to adjust in a way so that the total change in utility is equal to zero. Can I use that to get the a rule for slope of a difference curve? Yes, I can. Here's the utility. Change good one, good two slightly, and compute the change in total utility. Change in utility is change in utility due to just good number one times the change in good one plus the change in utility from change in good number two times the change in good two. Of course, you know from micro this is marginal utility good one. You know this is marginal utility good number two. And along the indifference curve means by definition all bundles with the same level of utility. So the change in the utility has to be zero. So your Q1, Q2 have to adjust in a very precise manner so as to offset, if Q1 goes up, your utility is going to go up. So Q2 has to go change in such a way so as to offset that change, negate that change. So you want this total change in utility to be equal to zero. Rearrange, and now you find out the total change in utility, the total change in good number two over change in good number one, holding utility constant, is given by minus marginal utility of good number one, marginal utility of good number two, which, if you remember, was called the marginal rate of substitution back in undergrad. Let's do an example. Here's a consumer with the Cobb-Douglas utility function. And someone says, give me the slope at a bundle Q1, Q2. If you did not use implicit differentiation, you would have to write the utility function term down in terms of Q1, Q2, since then you would have to rearrange Q2 in terms of Q of everything else. So you are able to obtain an explicit function of good number two in terms of everything else. You would then differentiate good number two with respect to good number one, and then you would get this monster. But now notice that you would have to plug in an expression for utility. So you'll have to plug in this expression right here, simplify, 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 make mistakes, and finally get this. But from the previous slide, you know that I can get the slope directly from minus mu1 over mu2. Here's your minus. Differentiate the utility function with respect to good number one. That's your marginal utility good number one. That's right here. Differentiate the utility function with respect to good number two. That gives you marginal utility good number two over here. You can see the Q1 alpha cancel off. Q2 beta cancel off. And in 5 seconds, you get this one right here, right? So this is a much, much faster rule for computing level slopes of level curves than doing it directly. Let's go back to the monster example we saw earlier. Nasty implicit function in terms of y, x's, and w's. This is what you're given, right? And now somebody says, give me dy dx and dy dw. Using the same trick we saw earlier, we now change y, x, and w simultaneously. And we ask ourselves, what's the change in the big F function when you change y, x, and w simultaneously? Well, first of all, you'll find out the change in the big F function with respect to y. That's partial derivative of f with respect to y times the total change in y. Then the partial of f with respect to x times the total change in x. Partial of big F with respect to w times dw. And you know that y, x, and w's have been changed in such a way so as to leave the whole change in the big F function equal to zero. Otherwise, that value would not eternally stay at zero. Now, somebody wants to say, give me dy dx. But if you want dy dx, you have to let dw be constant. Holding dw constant, setting dw equal to zero, since w is constant, you get that dy dx is minus f of x over f of y. This means you take this big F function, right? let's actually use a pointer right, so pen right. Take this big F function, and now you want to differentiate just with respect to x, right? So you should do this. Just with respect to x, this will be 2y cubed x, 2y cubed x, plus wy. And then divide by, take the f function and differentiate with respect to just y. That'll be 3y squared x squared, 3y squared x squared, plus wx. Exactly what you see here, right? So you can see that it works beautifully. So you're able to find dy and dx, even though you could not isolate y in terms of x's. And I'll leave this, of course, as an exercise. It's pretty obvious what we're doing over here. Now, if we're doing implicit function theorems, let's go back to implicit function theorem. It gave us a very clever way of finding out the things that are defined implicitly. You wonder if the y is a function of x in some neighborhood. And you saw that there was a technique that we could use to say yes or no. Can we do the same thing for implicit functions and implicit vector functions? We might as well do them and get them out of the way. Now what you have is, I'm going to do a slight digression. Now, I really apologize, guys, I'm sorry, but we have to be very careful about notation right now. Imagine that you have an n equation, Nancy equation, and these Nancy equations are in n Nancy variables. Okay, we're going to define a brand new matrix, so we already know what the gradient vector is. That's for a multivariate function with one y, several x's. This is called a Jacobian matrix. Jacobian matrix says give me the matrix of partial first derivatives. So this says what in plain English? Take the first equation, differentiate with respect to x1. Take the first equation, differentiate with respect to x2. And keep going until you take the first equation, differentiate with respect to x7. The last uh, line here means take the nth equation, differentiate with respect to x1. And you keep going until the nth equation, differentiate with respect to xn. Okay? So this is again a square n by n matrix. And now I'm going to make a distinction between variables and parameters. It's a digression, but the next lecture, lecture D, is going to be all about variables and parameters. Imagine, for the sake of illustration, that a certain product has a linear demand curve. So price is on the y-axis, Q is on the x-axis, here's the intercept, slope. Now, there are, depending on what your mission is, you can tell the reader something about the demand curve in many, many ways. You could say, simply, price is equal to A minus BQ. You could try to emphasize the role of quantity and point out that the price that you charge ultimately depends on the quantity you produce. So you could say price is a function of Q. They're all the same equations, by the way. It's just that when you write this way, you're emphasizing just the role of Q. But you also realize that the price of something not only depends on how much you're selling, Q, but also the values of these parameters A and B. A in particular, of course, is the highest price customers are willing to pay. So surely, if this baby A changes, the price that customers are willing to pay will also change. So to stress that point, you could say the price is in fact a function of not only how much I produce, that's the variable, but notice that semicolon parameters. Going into a problem, the A's and B's are being held constant, but you realize that down the road in real life, A's and B's could change. So the first things before the semicolon are variables that you can change at any given point. A's and B's are parameters that at any given point, when you solve for a Q, are held constant, but down the road could change. So this simply reminds the reader that price is a function of variable Q and parameters A and B. And if parameters get very many, you could collect all parameters into a set called alpha. So many ways to state things. Same thing over here. The revenue function, P times Q. You can leave it like this. You could remind the reader that it's a function of Q. As Q changes, revenue changes. You can also remind the reader that the revenue depends on not only how much I produce, but the parameters A's and B's. So now we're going into a different universe where we're dealing with variables, but we're also dealing with parameters. We now want to see what's the implicit function theorem for when you have several equations in several variables and now several parameters. Be very careful with changing notation now. You have n implicit functions and n variables. Those are your y's, see? y1 through yn are the variables. Notice there's a semicolon. And now the x's are parameters. So the x's are your a, b's, c's, and d's, which are as the previous slide, and the y's are your variables, as in the quantity on the previous slide. Given so many equations, you wonder, is y in fact an implicit function of the x's? Notice that what was the answer in previously? The answer was first, if you were only given one equation, you said first make sure they have continuous partial derivatives, then find a place where this entire function is equal to zero, and then ask yourself if the partial derivative of y was not zero. But now, since you have several y's and several x's, you just have to extend that result to, to several dimensions and several equations. So what you now want to say is all these equations will have partial derivatives in y's. They must exist, right? And there must be some point where those partial derivatives of y are not equal to zero. So lo and behold, the way we do this is we take the Jacobian matrix, which was the matrix of first derivatives. So previously we said that if you only had one y variable, you were insisting that the partial derivative of the implicit function with respect to the y was not equal to zero. But since you now have several y's, it's not saying that you should have each element be equal to zero. Right? Rather, what you're saying is that the determinant of this Jacobian matrix must not be equal to zero. So you really want to go back to the univariate case. Previously, you said this derivative must not be equal to zero, right? For y to be a function of everything else. Now what you're saying is the entire matrix determinant must not be zero. If that's actually true, and there's a point x0, y0 where these things hold with zero zeros, then you are implicitly defining y's in terms of x's. So you're guaranteed that there is a relationship between all the y's and all the x's, even though you don't know the precise relationship. Here's an example. It's a simple macro model. GDP is equal to consumption plus autonomous investment and government spending. I think I said previously this could be like North Korean economy. Investment is fixed, government spending is fixed. Consumption is Keynesian, alpha plus beta times disposable income. Taxes are proportional to GDP. Notice that if I rearrange these equations as I did so, I think previously, you get three implicit functions. And remember the variables were GDP, consumption, taxes. So you get three implicit functions, right? And three variables, y, ct, y, ct, y, ct. And these parameters, investment, you see the semicolon, investment, government spending, alpha, beta, gamma, delta, right? So these are your implicit functions, three of them. So you're given these equations right here, over here, right? So notice that what I'm about to do is beautiful. I'm about to do some interesting things without ever having to solve for y, c, and t. Here are those implicit functions right here. Three implicit functions and three variables. I wonder if this system can be solved. What that means is, before I even start going down this road and start solving these crazy equations, is it really true that there is some possibility that y could be ultimately expressed in terms of parameters? Is it really true that I can solve for consumption in terms of all these parameters? Is it really true that I can solve for taxes in terms of all these parameters? Can I solve the system ultimately in terms of, for the endogenous variables in terms of parameters? Implicit function theorem says that this Jacobian matrix, the determinant of this must not be zero. Well, what's this? So there are three variables, three equations. So you would differentiate the first equation with respect to the first variable, which is GDP, first equation with respect to second variable, which is consumption, and first equation with respect to taxes, which is this thing right here. Same thing with the second equation, differential with respect to y, c, t. Third equation, differential with respect to y, c, t. This determinant must not be zero. Right? So first of all, these things exist because you can see that what's the first equation, differential with respect to y? Well, let's see. First equation with respect to y is, notice right here, 1. 1. First equation with respect to consumption, minus 1, minus 1. Sorry. First function with respect to taxes, okay, you know what, forget this. First equation respect to taxes. You don't see taxes here, so the derivative is 0. Right? And just to make sure we don't get lost, second equation with respect to GDP. If I differentiate the second equation with respect to GDP, the answer is minus beta, minus beta. Second equation with respect to consumption, you can see the answer is plus 1. Second equation with respect to taxes, the answer you can see is plus beta. Third equation with respect to GDP, minus delta. Third equation with respect to consumption, 0. Third equation with respect to taxes, 1. And when you take the determinant of this thing, which of course you know how to do, you get this. I want, as long as this expression is not equal to 0, right, then you are guaranteed, since these things are always equal to 0 the way they are actually arranged, since as long as this is not equal to 0, we are guaranteed that there is some point out there where I can solve for y in terms of parameters, i.e., we are able to solve the system and express y's in terms of all these things. Beautiful, no? So before I start solving crazy things, I have to make sure this determinant is not equal to 0. But if you really want to do well on the test, wait a second, this must have looked very familiar. Don't you remember how this was the same thing as the determinant of that matrix A? Remember how we expressed the system as AX is equal to B? So this is the identical result that we got that way, right? But now from a different perspective. So we know solutions exist. In fact, I use Cramer's rule to derive them. But right now, I'm going to go a bit further. Without solving for y, c, and t, I'm going to do comparative statics, i.e., how will GDP consumption taxes change if any of these parameters was to change? That's an example. Here's an implicitly defined macro system. I wonder what will happen to y, c, and t, my three endogenous variables, if, for example, if government spending goes up, one-time impulse increase in government spending. The one-time increase in government spending, without ever solving for GDP consumption taxes, can I predict what's going to happen to qualitatively at least, to GDP consumption taxes? The way to do this is exactly what you've been doing earlier. The trick now is you have to say, wait a second, what's changing here? Well, G is changing, and it's ultimately going to cause a change in YCT, because you know from the previous slide that YCT are implicit functions of these things right here. So when G changes, I know YCT will change. Let's do that. So let's imagine now YCT and government spending change. Then the first equation, the total change in the first equation, is the change in the first equation with respect to GDP. That's right, the change in this thing right here. You know what? I should not have used the symbols DF. I'm sorry. I take it. It's actually sorry. I apologize, guys. So I should not have used in my actual lecture that I'll upload. I'll take out these over here, right? Because you simply want to differentiate the f function with respect to y, right? So my apologies. So what's the change in the first f function with respect to y? Take the partial derivative of the first f function with respect to y times the total change in y. Differentiate the first f function with respect to consumption times the total change in consumption. Differentiate the first function with respect to taxes times the total change in taxes. And then let's not forget that you're also changing g, so the partial derivative of the f function with respect to g times the total change in g. And since no other parameters is changing, all those other terms are going to be equal to 0. I know that the total change has to be equal to 0. I do the same thing for equation number 2, equation number 3. So this is what we have here. And again, I want to apologize. I remember these and the actual lecture slides I post are not going to be there. In the video, they are there because that's the way it is. If I now take the previous, this thing right here, and I move the DG terms to the right hand side, I get this thing right here. And now what I want to do is I'm going to divide by DG throughout. And now this starts to give me these expressions right here. See? And now again, remembering that the D's here are a typo on the video at least. You notice that, voila, right? You can rearrange this matrix. Remember that these are a typo. So these are partial derivatives right here. I can take this system right here and express the matrix form exactly as you see over here. Beautiful. So the previous slide, this you can express as a matrix multiplied by this vector right here. See, all these are your derivatives. equal to ta 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 right over here. And now, of course, I know that what's the f first equation, differential with respect to y. That's exactly what you saw earlier. 1 first function with respect to c. Here's your -1. So nothing has changed. So using those equations, I can give values over here. And then, of course, I can use Cramer's rule to solve for the dy dg, right? dc dg and dt dg by using Cramer's rule, right? Now we go to quote unquote concave, convex, quasi concave. This is very messy. Let's just start slowly. The idea here is let's start with the univariate case. Okay? A strictly concave function. So the best way to remember this is imagine you're riding a roller coaster. If you always have the slow sensation that you're always slowing down, you are on a strictly concave function. If you have the sensation of slowing down or moving at a steady speed, you have a concave function. Strictly concave is the sensation of always speeding up. Convex functions are speeding up and or steady speed. A function that's concave and convex, because you can see that steady speed appears in two possibilities. If you're always moving at a steady speed, you must be in a function that's simultaneously concave and convex. And if neither of these things are happening, which means you're sometimes going up and sometimes going down, you must be in a function that's neither concave nor convex. Some examples. If I'm riding a roller coaster, I would always have the sensation of slowing down, strictly concave. Here I'm slowing down or moving at a constant speed, concave. Speeding up, strictly convex. Speeding up or moving or steady speed, convex. Always moving at a steady speed, concave and convex. Sometimes going up and down, that's neither concave nor convex. So if you're given an equation and asked to say, is it strictly concave, strictly concave, concave, strictly convex, etc., etc., you would say, wait a second. If a strictly concave function is always slowing down, you would be tempted to say that the second derivative must always be less than zero. It's a temptation. And if a strictly convex function gives a sensation of always speeding up, you may be tempted to say the second derivative must be always strictly positive. But as you're about to see, that's not true, because you could have a strictly concave function even though the second derivative is not zero, not always negative. Here's an example. The one downside of Wolfram alpha is that when you plot functions, uh, they tend, because of the graphics things they use, things look flat over here, but they're not really flat, right? Because you're looking, it's just the way it's drawn. So this is the function of minus x to the power 4. It is in fact literally a curve right here. It just looks flattish because of the crappy graphics that Wolfram alpha has. Is this function, so notice that if you're riding a roller coaster, you would always essentially slowing down, right? Yeah, slowing down, right? So if that's the case, is this, would you have said the second derivative is always negative? Well, not really. What's the first derivative? Minus 4x cubed. Second derivative then be minus 12x squared. And now notice that minus the second derivative at the point x0 is in fact equal to 0. So second derivative is negative everywhere except the point 0. Yet intuitively this function is strictly concave because you always have sense of slowing down. So notice that if you want to define things rigorously, and I'll leave the strictly convex for you, it's done. You should do it this way. This is extremely important that you get this. Let's make sure that we have the following. If the second derivative is always less than or equal to 0 for all values of x, it means the function is concave, which means it's slowing down and or moving at a constant speed. If somebody tells you the function is concave, you can then tell me that the second derivative must be less than or equal to 0. If the second derivative is always negative, if you always have the sensation of slowing down, that function must be strictly concave. But as the previous slide shows you, a function can be strictly concave and not have a second derivative always be negative. So notice the arrow points this way. If I'm always slowing down, I am strictly concave. But if I'm strictly concave, I don't always have to have the sensation of, well, don't always have to have the second derivative be strictly negative. And those are the analogous results for convex and strictly convex functions. So this characterization of concave and convex and so forth relies on derivatives. You wonder if there's another way to characterize strictly concave functions without using derivatives. And I do this only because you will have to use this for decision making under uncertainty. You might remember from back in undergrad, risk averse agents, risk loving agents, risk neutral, insurance, etc., etc., etc. You can read the text carefully on your own, but here's a way to characterize a concave function without using calculus. It's a very fancy way of saying something very simple, which is you'll see in a few seconds. What you see here is the function minus x to the power 4. What first says take two values of x's. Here's the value of the function at x1. Here's the value of the function at x2. Now, imagine a weighted average of x1, x2. A weighted average by definition somewhere should be somewhere on a straight line connecting these 2 points, somewhere in between. And now ask yourself, what's the value of the function at this weighted average? So what's the value of the function at this point? So this will be, of course, the function evaluated at the weighted average of x1, x2. And now ask yourself, here's f of x1, here's f of x2. What's the weighted average of those 2 points? Any weighted average must lie on a straight line connecting those two dots. And if I this is the ratio of alpha 1 minus alpha, that weighted average must also be the ratio of alpha 1 minus alpha. So it has to lie on a point right underneath. So this green dot is the weighted average of f of x1, f of x2. Whereas this one is a function of the weighted average of x1 and x2. More formally, here's the weighted average of x1, x2, alpha x1, 1 minus alpha x2. Here's a function evaluated at the weighted average of x1, x2. Here's f of x1, f of x2. Now take a weighted average of these 2 points, put alpha weight on f of x1, put 1 minus alpha weight on f of x2. Now notice what the definitions say. If, it's easy to read on the previous slide, if the function evaluated at the weighted average of x1, x2, if the gray dot is always bigger than or equal to the weighted average of f of x1, f of x2, if this gray dot is always bigger than the green dot, that function is concave, and also the other way around. And if that weighted average is always strictly bigger than this weighted average over here, if this gray dot is always bigger than green dot, always strictly bigger, then that function is strictly concave and vice versa. So you have to ask yourself, when it comes to strictly concave function, what must be true so that the green dot is always below the gray dot? Well, it must be true that if you pick any 2 points on the function, the arc always lies below the curve. So the rigorous definition of strictly concave functions, ironically, is that if the arc connecting any 2 points of the function, if that arc is always strictly below the curve, that function is strictly concave. And if the arc is strictly below or touches the curve, that function is concave. So that's a very fancy way of saying simply a strictly concave function has an arc that's always below the curve. And I leave this as an exercise for you to understand that the reverse must be true for convex and strictly convex functions, where the arc connecting any 2 points on the graph must always be above the curve for strictly convex. And the arc must be either above or touch the curve for simply convex functions. Right here. So let's summarize. Using the univariate example as an illustration, you now know that if I go back to this, the calculus-based ways to characterize convex, concave, strictly concave, and strictly convex functions, here's what we say. If the second derivative is always less than or equal to 0, that function is concave. And if you tell me the function is concave, the second derivative must be less than or equal to 0. What's the counterpart of this in many x's? Well, less than or equal to 0 in the case of multivariate is of course negative semi-definite. And what's the counterpart of the second derivatives in multivariate? The Hessian matrix. Here, if the second derivative is always strictly negative, that function is strictly concave, but not necessarily the other way around. What's the analog of strictly negative in multivariate? Negative definite. So if the Hessian matrix is negative definite, that function is strictly concave. But if the function is strictly concave, it need not have a Hessian that's always negative definite. Now leave the other last two lines for you to read on your own. So we now have a multivariate. Remember how to sign a matrix to see if it's uh, PD, PSD, ND, NSD, and so forth? Well, I'm just reminding you how to do this. Now, let's check if this multivariate function is concave, convex, strictly, all this stuff. Let's see. Here's a function right here. Let's do the gradient method first. Let's see. So when you differentiate with respect to x1, that's 2 right there, minus 2x1, and plus 2x2. Differentiate with respect to x2, minus 1, plus 2x1, minus 2x2. Now take the Hessian matrix. First differential with respect to x1, that gives you minus 2. Differential with respect to x2, that gives you 2. By Young's theorem, I does the same things over here. And now I differentiate with respect to x2, and the answer is minus 2. And now the question is it concave, convex, strictly convex, etc. So we have to find out what the sign of this matrix is. To do this, I look at the leading principal minors. So I notice that the first leading principal minor, which is this thing right here, is negative. So right off the bat, I know there's no way this function can be strictly convex, or for that matter, convex, right? Because you would need to actually have those things be bigger than or equal to 0 or bigger than 0. So since it's actually strictly negative, it's possible that this thing is concave or strictly concave. But now when I look at the second leading principal minor, I notice that that determinant is 0. So I now notice that, wait a second, so I'm unable to conclude that this is negative definite because this is equal to 0. So for that, to make a conclusive, this is actually really, sorry. This is what happens when you do lectures at 5:45 a.m. To get the right insights, you then have to look at the principal minors. So there's principal minors here. Remember the diagonal elements. So there are two first order principal minors. One's in diagonals, minus 2, and then this principal minor, which is 0. Right? So notice that the first all odd numbers leading principal minors and principal minors are negative, and all even numbered principal minors are 0. Therefore, this function is negative semi-definite or concave, but not strictly concave. Let's go to quasi-convex functions and so forth. To do this, we have to talk about something called convex sets, upper level sets, lower level sets. Intuitively, by the way, there's no such thing as a concave set. A convex set says, take a set. If you can take 2 points, any 2 points in that set, if the weighted average, also known as the convex combination, is also in the set, then that is a convex set. So it doesn't matter where I pick A and B. Any place where I pick points A and B, the weighted average of those 2 points will always be in the set. This is not a convex set because if I chose these 2 points A, B, those weighted averages are in the set. But had I chosen those A's and B's, some weighted averages are outside the set. So that's not a convex set. This is again a convex set because no matter whether I choose A and B, it's always weighted averages are going to be always in the set. So a convex set is ruling out jagged edges. It has to be smooth, right? These things. Now we do something a little bit different. Upper level sets. And I'll use a single variable function to illustrate what that means. Let me use a marker. Okay. It says, an upper level set says, these are all the x's in the domain such that the value of the function is bigger than or equal to some number a. So what it works is, pick a value a, any number. So I could pick something here, right? And ask myself, for which values of x is a function below this yellow line? Well, none. What if I pick this value of x, of a, sorry. So I wonder for this value of a, where is the function, for which values of x is a function higher than a? So the answer is, this is where the function is greater than or equal to a. and the values of x's that correspond will give you this are right over here. So the upper level set are these x's, because only for these values of x's is the function above a. In the same way, here's the function above a value a, here's a function above a value a. And so your upper level set, of course, are these x's and those x's. And over here, this is where the function is above a certain value a, and again the function is above a certain value a, and you wonder what are the corresponding x's. These are the x's, those are the x's. Now ask yourself the question: are these x's these x's so that the value of the function at those x's is bigger than or equal to a? Is this a convex set? Meaning that if I pick two x's in this, if I pick 2 points in this, are any weighted combination of those 2 points in here a convex, always in the set? Yes, right? No matter which 2 points I pick in this orange region, any weighted average will be always in the orange region. But this is not a convex set because right now the upper level set is a union of this segment A and B. If I choose a point in this segment, and if I choose a different point over here, some weighted average of those 2 points are going to be outside the upper level sets. So this upper level set is not a convex set. Neither is this upper level set. Lower level sets, by same analogy, now it says, give me the values of x's where the function is below a certain value of a. So here's where I'm below a certain value of a, below a certain value of a. These are all the x's that will give me and guarantee the function is below a. Same thing here. The function is below the value of a, and these are all the x's that will give me that value of function. And this is where the function is below the value of a, below the value of a, and those are the corresponding x's right here and here. And now again we are asked this following question: is this orange set a convex set? No, right? Is this orange set a convex set? Yes. Is that orange set a convex set? No. And so we now have a definition. Consider upper level sets. A function is quasi-concave if every upper level set is a convex set. So, right, a function is quasi-concave if every upper level set is a convex set. So is every upper level set a convex set? Yes, convex function. Is every upper level set a convex set? No, can't be quasi function. Is every upper level set a convex set? No, this can't also be a quasi concave function. And by the way, every concave function is a quasi concave, but not necessarily the other way around. Quasi convex looks at lower level sets. A function is quasi convex if every lower level set is a convex set. Is this lower level set a convex set? No, cannot be a quasi-convex function. Is this lower level set a convex set? Yes, it is a quasi-convex function. Is this lower level set a convex set? No, it's not a quasi-convex function. What about in multivariate cases? So I'm going to extend this definition now again to, let me use the, my mouse does not want to be here. All right. Actually, let's use a different color. Let's use purple. There we go. In multivariate cases, upper level set are all those x's for which the function takes on a value bigger than some value a that you choose at random. A quasi-concave function has a property that every upper level set is a convex set. Oh my god, what does that mean in plain English? You have a function of x1, x2. So imagine a third axis coming out of slide. These are the projections of the contour plots, and now every one of these contour plots corresponds to a height on the 3D surface. Let's imagine that this contour plot is of height A behind the scenes. What's the upper level set? For which values of x? So remember the arrows pointing this way, which means the mountain is going up in height this way, right? Going northeast. Which values of x will ensure that the value of the function for those values of x's are bigger than or equal to a? So everyone agrees that, so I'm not going to color everything, but any value of x1, x2 in this region will ensure that you achieve a height greater than or equal to a. And if I were to fill this completely, will this be a convex set? Yes, because if I picked any 2 points as purple thingy wingy, any weighted average would be within that set. Here's a level curve right here. What's the upper level set? It's all those things over here, right? So this entire region right here. Sorry, as you can see, I should not have done this, but you get the point. Is this set a convex set? Yes. Okay. And now remember that the arrow is pointing up this way. Here is the level curve for A. Is what's the upper level set? It's all those x's that you see and right and going this way, in this direction. Is this purple region a convex set? No, because I can pick a point right here, and you can see that if I do a weighted average, some weighted average is going to be outside that set. So upper level sets are convex, therefore it's a quasi-concave function. Upper level sets are quasi-concave, therefore it is a quasi-concave function. Upper level sets are not convex, therefore it's not a quasi-concave function. In the same way, a quasi-convex function, if you remember, was if every lower level set is a convex function. So this is now the one who corresponds to height A on the 3D surface. The heights are going up in this direction. The lower level sets are all the x1, x2s over here. Clearly, that's not a convex set because, for example, this weighted average lies outside the set. Here's the level curve for A. All these x's are the lower level sets. That set is, in fact, a convex set. And what about this one? The lower level set, of course, are all x1, x2 combinations right here. That is a convex set. So this is a quasi-convex function. So is this, but not this. So notice that there is some quasi-convex functions can coincide with quasi-concave functions that are both quasi-concave and quasi-convex. And by the way, every convex function is quasi-convex, but not necessarily the other way around. How do we check this? Well, imagine you're given an equation of y in terms of x's. So now what we have is a completely different animal. We now have a weird border Hessian matrix, where this is 1 through n. So if there are n variables, there'll be n of these border Hessian matrices. The first element right here is always going to be the number 0. Okay? So this one, you can see they're getting bigger, right? So here's how you do it. Suppose there's a function, a multivariate function, defined on x. Consider the border Hessian matrices, where is the determinant of this border Hessian, where k goes from 1 through n. When k is equal to 1, you get what you saw in the previous slide. When k is equal to 2, you get what you saw in the previous slide, right? And etc. They get bigger and bigger. Here's the way you check for quasi-concave functions. Focus on red lines. If the odd numbered border Hessians determinants are negative and the even numbered border Hessians are positive, then we have a quasi-concave function. And if all border Hessian determinants are negative, we have a quasi-convex function. Incidentally, notice that this one says if the first border Hessian has negative, it's quasi-concave. Right? This is also says if all border Hessian determinants are negative, it's quasi-convex. Notice that the determinant of this first one will always be 0, because 0 times this minus that times this minus f1 prime squared is always going to be a negative number. So no matter what, this first d1 is going to be negative. So when you do the first border Hessian determinant, it's going to be negative. But if the second one turns out to be positive, and then flip-flops alternates the sign, always with strict strictly positive, strictly negative, strictly positive, negative, and so forth. And if all these are strictly negative, this is quasi-concave, that's quasi-convex. Example, y is x1 times x2. The first board Hessian determinant, like I said 2 seconds ago, is always by definition going to be always negative. Has to be. What about the second one? If you work it out, you notice it comes out to be like this. If I now define x, this function is defined for x1, x2 being bigger than or equal to, well, bigger than 0, then notice that the first board Hessian is negative, the second one is positive. So there's no way it can be quasi-convex. For quasi-convex, I need all board Hessians to be strictly negative, right? But is that quasi-concave? Well, yes, if as long as x1, x2 are strictly positive, it is, right? Because the first odd numbered one is negative and the even number one is positive. And now we're asking the question, it's a quasi-concave function, but it's not a concave function. Because for a concave function, what did you need? You needed the Hessian matrix to be negative, semi, definite, right? So if you actually play around with this, notice that if you take this as an exercise, you can show that it will not be concave because, well, you can see right off the bat that, let's see, it's not concave because, okay, so notice that the diagonal elements of the Hessian matrix are 0, right? So it could be negative semi-definite. And then the Hessian matrix has determined that's equal to -1. But the Hessian matrix, of course, is the second principal minor, right, over here. And that if it was going to be concave, would have had to be positive, not negative. So it's not concave. This is a chart. It's not complete. Sorry, it's still a work in progress. That's an appendix giving you different ways of looking at quasi concave and quasi-convex functions. Nothing to worry about right now. And I think with that we're done. Thank you so much.